All right, back again. Ready to drop some fire with these videos, and I was told by several of you I need to have a good YouTube introduction. So here it is. Yo, 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 what's up? I'm back again. Something like that. But anyways, what I want to do today is I want to show you in this video is basically how to do the three most common types of Atwood machines. And what I've chosen to do essentially is to take the three hardest versions of each of them. So basically what we're going to see in this video is we're going to see a standard Atwood machine with more than two masses. We're going to see a modified Atwood machine with more than two masses, and then we'll also see one on a ramp with more than two masses. And in every example I'm going to add friction as well, since I consider that probably to be the hardest iteration of each of those. Okay, so here we go. We're going to start out with, like I said, a standard Atwood machine, and this is going to have multiple masses. So kind of here's what I'm thinking. Okay. Also, I'm not going to use any numbers on this. I'm just going to be basically just doing the variables, solving for those. Okay, so here we go. Here's my Atwood machine. Okay, I'm going to put multiple masses on there. Okay, and to kind of throw a little bit of something interesting in there, I'm going to actually make this side the heavy side, and then this side over here is going to be my light side. Okay, so I'm going to call this one mass 1, mass 2, and then mass 3. Okay. So here's what we know. We know mass 1 is going to be greater than mass 2, which I guess it can be greater than mass 3. Doesn't really matter. Okay. So here's what you want to do. I can't stress enough how important it is to kind of work through these and to do it very methodically and to work them the exact same way every time. So what I want to do is I'm going to basically do a free body diagram for each of those. Okay, so here's my mass 1. Okay. All right. We know it has a weight. I'm going to call this weight FG1 for mass 1, and then we also know it's going to have a force of tension on it. Okay. Do something similar for mass 2. Okay. Mass 2 is a little bit weird. It's going to have actually multiple forces kind of going down on it, because you've got the weight of mass 2, but you also have what I'm going to call tension 3 acting on it. So you actually have two of them going down, and this is what makes these a little bit trickier. Okay, and then going up we have what I'm going to call FT2, because it's string 2. Okay. Now one thing for sure is when you are doing these, if it's a single string like for example 1 and 2, this really isn't two different strings, it's actually just the same string. So we can safely assume that the tension is identical. So really FT1 and FT2 are really the same thing. Okay, they're all the same thing. Okay, now after we do the diagrams, or before, it doesn't really matter, we're going to determine which way this machine is actually going to move. So if this is the heavy one, based on what I said earlier, then the machine is going to basically rotate this way. And that's going to be my positive direction. Okay? And the reason that is so important is we're going to basically do Newton's second law statements based on that assumption. Right? So here's what we know. We know the sum of the forces on the system equals the mass of our system times the acceleration of our system. Okay? All right. So then what we'll do is we're going to basically do a Newton's second law statement for every single object within the system. Since I have three objects, I got to do three additional statements. So I'm just going to do them in order. Sum of the forces on number 1 equals mass 1 times the acceleration of the system. Okay. So I'm looking at my diagram for number 1, and I see on the diagram that basically I've got FT1, FG1. FG1 is going in the positive direction. FT2 is going in the negative direction. So FG1 is my positive, and then my negative is FT1. Okay? All right, same thing for number 2. I've got mass 2, I've got acceleration of the system. Okay? Now, mass 2 is a little bit, well, it's complicated because it's got a lot of stuff going on. Okay? Mass 2's got a tension, it's got weight, it's got another tension, so I've got to be very careful. Okay, keep in mind the flow from this diagram right here is going to tell us whether these are positive or negative. So here's what I got. I've got positive FT2, which is actually FT1 based on what I said earlier. Okay, minus FG2 minus FT3. Okay. All right. Number 3, I forgot to do the diagram earlier, so I'm going to go ahead and do it right now. Okay. This is M3. It's got the weight of FG3 pulling it down, and then it's got FT3 pulling it up. Right? So mass 3 times the acceleration of the system equals FT3 minus FG3. Okay. So now basically I have all the statements I need on here. So what I'm going to do now is basically going to kind of simplify all these and then put them back up here in this equation. Okay? So all the tensions cancel out. That's nice. So really, here's what I have left over. Okay? This tension is going to be canceled by that one. This one's going to be canceled by that one. So here's my statement. It's going to be basically FG1 minus FG2 minus FG3. Okay? So if I want to ultimately solve for the acceleration of the system, I can do some pretty basic algebra now. I'm going to go ahead and show you that. And then at the same time I'm doing that, I'm going to go ahead and get rid of those F's because, like I've said, you can't really do anything with the F, so we got to get rid of them. Right? So here we go. We have the acceleration of the system equals M1G. That was our FG1. Minus M2G, which was FG2, minus M3G. And all that's going to be divided by the mass of our system. And our system consists of masses 1, masses 2, and mass 3. Okay. So that's the acceleration of this particular pulley. Now, occasionally we ask questions like to solve for the tension, like to solve for tension in string 2 or string 3 or something like that. And if that's the case, it's not hard at all. You just basically go back to one of the equations, whichever you're trying to solve, and then you will just basically plug it in. So let's just say, for example, just to show you, I'm going to solve for the tension in string 3. Okay? So what I'm going to do is I'm going to go to either one of those two equations. I like this one mainly because it just looks easier. It doesn't have the negative in front of the FT3. So here's my solution. Okay? It will look like this. M3 times, and I don't want to write all this again, but basically all of this is the acceleration of our system. So basically, I'm just going to do this because I can. Okay. All of that times M3 equals FT3 minus FG3. Okay. Now, pretty basic algebra. I just got to move this over to the other side, and then when I do that, I will have my expression for FT3. So I'm just going to plop this back over here. I'm going to add FG3 to that side, and then lo and behold, I have my answer for FT3. Okay, so that was a simple simple Atwood's machine. Now I want to look at a modified Atwood's machine. Okay. So the modified Atwood's machine is a little bit different. We've talked about that in class, why it was a little bit different. But here we go. We're going to have a situation like this where we have multiple masses hanging, or actually not hanging, but on the actual table. Okay, and we're going to add friction to the table. Okay, so this has got friction. It's very much possible that this one could have different friction to that one, but I'm not going to show that. That this will be our mass 1, that's our mass 2, and that's our mass 3. Okay. So if this is gravity powered, it's going to move that way naturally. Okay. This is our positive direction. All right. So now I'm going to do my free body diagram. Okay. This is my mass 1. This is my mass 2. And then over here will be my mass 3. Okay. All right. Mass 1, we know it has Fg1, force normal of number 1, This one has FG2, force normal of number 2, and then last but not least, FG3, FN3. Okay, so lights went off, so I'm going to go up and take a little break real quick, do some calisthenics, get the blood flowing. Come on, lights. There we go. Good. Got that going. All right, back again. Okay, so we've got all those forces on there, but there's also some other stuff too. We don't want to forget the friction and the tension and all that good stuff. So here we go. I'm going to go ahead and label those strings 1, 2, and 3. Okay. Keep in mind from the last example, since this is actually a single string, there's really not a different tension in those. Okay, don't let that fool you, and they will try to fool you that way. So here we go. We got force of friction of number 1. And then I'm going to call this one FT1. Okay, for the force of tension string 1. Okay, this one, we got multiple forces, so be careful. This is friction for number 2, but we also have the FT1 on there. You got multiple forces on there, don't forget. Then this one, mass 2, is being pulled by force of tension of string number 2. Okay, now I just realized this, I made a mistake. I call that force normal. That's actually not a force normal. This is the hanging weight, so this should actually be FT3. But remember what I said, FT2 and FT3 are really the same thing, so we'll just have to keep that in mind here in just a moment. Okay, so those diagrams are pretty ugly, pretty complicated, pretty kind of, I don't know, just all around not very pretty. Okay, so what I want to do next then is I'm going ahead and make my Newton's second law statements. Okay, so we can actually do some solving with this. Okay, so here we go. Sum of the forces of my system. Okay. Mass of my system times the acceleration of my system. Okay. Now, occasionally, the system will not be accelerating. It might be at rest. Like you might see problem structure in such a way as solve for the friction or something like that. And if that's the case, if this thing is not accelerating, then keep in mind we would set this equation equal to 0. Okay, so do keep that in mind. Okay, but this time we're going to assume it's actually accelerating, so we don't really know what it equals yet until we do the other statements. Okay, so the sum of the forces of number 1 equals mass 1 times the acceleration of the system. Okay. All the forces acting on 1. Now, we don't really care about the FG and the force normal. Those are not affecting the actual acceleration. We only care about the accelerations that are either with, or excuse me, the forces that are either with or against the flow. So here's what we have. Force of friction is against the flow, so I'm going to make that a negative. Force of tension is with the flow. Make that a positive. Okay. Moving on to the next one. Number 2. Mass 2. Acceleration 2, or actually system. And here we got multiple ones going backwards. We've got tension going backwards. We've got friction going backwards. So force of friction of number 2 minus the force of tension number 1. And then plus force of tension from string number 2/3, whatever you want to call it. Okay. All right. Still not done because we've got multiple masses, got multiple statements. Okay. This is the one that's hanging off. So we just have, well, force of tension 2/3, and then I'm going to just do that one, same thing, because those will cancel. We want those to go away here in a minute. Okay. Plus FG3. Okay. So here we go then. So just like last time, we're going to cancel out those tensions because they are an internal force. They don't really matter. We just care about the external forces. So here is going to be my grand statement once everything has been kind of put together. Now, I'm going to go ahead and get rid of the mass of the system and go ahead and call it what it really is, which is mass 1 plus mass 2 plus mass 3. All right. Is going to equal, well, those tensions cancel. That tension cancels. That one cancels. So really, my external forces is the weight of number 3 and then the frictions. Those are the only forces that are external to my system. Okay. All right, that was a positive. Force of friction 1 was a negative, as was number 2. Okay. Oh, I just realized I forgot something over here. This should be times acceleration of the system. Okay. Alrighty, so I'm going to go ahead and do the algebra here real quick for this and go ahead and get rid of all the F's as well. And it's going to be pretty nasty numerator, but we'll deal with it. Okay. So acceleration of the system, okay, is going to be equal to, go ahead and get rid of the F on that one. That's going to be M3G minus the force of friction number 1, which is mu times mass 1 times gravity, and it's actually cosine theta, but since we're on that flat surface up here, it's really just going to be 0 degrees, so I don't really want to put it on there. Okay. All right. And then force of friction 2, mu m2g. Now, if there's different mu's, you would need to address that here. Like if the mu of that box is different than the mu of that box, make sure you know the difference between the two of them. Also, don't forget that the friction's acting on different masses, so you want to actually not use the same mass with the same thing. So that's our numerator. It's pretty ugly, but we love it all the same. All right, on the bottom, mass 1 plus mass 2 plus mass 3. Okay. Now, occasionally they'll ask you to solve for tensions. I don't think we really need to show that again because we did basically it's the same thing in the last video. You figure out which equation you want to use, which tension you want to solve for. Like if you had to solve for tension 1, I'd probably use that equation because it's nice and easy. If I wanted to solve for tension 2/3, I would probably use that one because, well, I'd probably use that one since it's got it as a positive number. Okay. But you just basically plug in the acceleration of the system, and then you can solve for tension that way. So, not too bad. Okay. All right, last but not least is going to be an Atwood's machine on a ramp. And these are notoriously difficult. There's really just no way to put it. Okay. So you have a ramp that has some angle of theta. Okay. Occasionally you have to solve for the angle of theta. And if that's the case, I'll point that out here in a minute how you would actually do that. So here's how I'm going to set this one up. I'm going to put 2 masses on the ramp and then 1 mass hanging off the ramp, kind of like that. Okay. All right. So this is mass 1, mass 2, and then mass 3. Okay. Call that string 1, and then really we could call this string 2 and 3, but I think we've already beaten that horse to death. It's actually just the same, so I'm just going to call that one number 2, string 2. Okay. All right, and to make it even more challenging, I'm going to add some friction between the boxes on the ramp. Okay. Okay. Start out the exact same way. We're going to make my statement that this is going to be my positive direction. Okay. And now I'm going to do a free body diagram for everything. So here's my